turn that down because we're in class, so that's going to be real distracting.
Okay, welcome everybody. Let's get started here. Your third assignment from Chapter 4 is due Tuesday of next week, and I've got one of these problems that I've got some key ideas that we'll go over today. We're beginning the last part of Chapter 4 where we're going to be talking about kind of a unique application of acceleration and the effect that has on pressure and elevation. But before we start on that, are there any questions from the recorded lecture that you watched on Tuesday, or questions maybe from the lab or anything else? No? All right. Well, let's talk about radial acceleration. And I've got a video just to kind of introduce the idea. Okay, so as we were just discussing, it's a radial acceleration. Yeah, Connor.
Why doesn't the water displace like the long sides of the tank as much as it does in the corners? Like if it's always going from the center from all sides, wouldn't it?
That's a really great question. I appreciate you asking that. So his question is, why is it higher in the corners than it is here, right? So anyone want to venture a guess why the liquid level rises more here than at the edge? It's further away from the center, right. And the magnitude of the acceleration must in some way take the radius away from the center of rotation into account. And that ends up being the case. We'll look at the equation that gives us radial acceleration, and it does, the magnitude of the acceleration is greater further away. That's why when I go on my long runs on Sunday, I wear like this vest and it gets really sweaty and gross. And so I hose it off when I get home. And then I swing it around in a circle to dry it. And it would probably be even better if I tied a little bit of a string to it so I could swing it like with a great radius. So the further away it is from me as you swing it, the more the acceleration is, and then the water just kind of splashes all over the place and it doesn't drip in my garage. So here in this case, that's a really good question. I'm glad you asked it. So we can see the effect that radius has on the magnitude of acceleration because the liquid level rises to the highest point where the acceleration is the greatest. So here, it's furthest away from that center point. And if we maybe go a few frames forward, we get that same view from a different perspective. All right. So that's good stuff. I need a high-speed camera. I'll try and convince Dr. Solom to get us something like that. We need more toys in the fluids lab. So here's the equation that we can calculate the centripetal acceleration, and we have these same units of length per time squared that we've seen in convective and local acceleration. So the units didn't change. Acceleration is still meters per second squared, even when it's something that's rotating in a circle. And it can rotate at a constant rate, and there's still an acceleration there. And so think about it. If it's spinning at some rotational rate, omega is how many radians per second the angular velocity is passing through. So we can have a constant rotational rate, and yet there's an acceleration there. So we can think of this centripetal acceleration in terms of the tangential velocity, and so this illustration is saying the tangential velocity is at the end of the radius, the velocity that's traveling, including direction and magnitude. So the speed and the direction of its speed at any particular point is tangential to the circle that's being drawn by its rotational path. And we square that tangential velocity, divide it by the radius, and we'll get the magnitude of the radial acceleration. Or we can have the angular velocity, which has units of just inverse seconds. And so although here in angular velocity we're saying it's radians per second, radians isn't really a unit. When we combine it with other things that do have physical units, it just sort of melts away and it's not there any longer. So if you look at rotational rate, the angular velocity, radians per second, so we're going to be squaring that, and that's where the second squared in the denominator come from. And then we're multiplying it by the radius from the center point of the circle that's being drawn to the outer edge where the particle actually is. So it'll be important in problems like these where sometimes you'll be given the rotational rate in terms of rotations per minute. That's a fairly common means of describing when things are moving in a circular or periodic fashion. The speed of that rotation is often RPM. And so you'll notice that we can't put RPM as our angular velocity. We have to convert that to radians per second. And so the conversion factor, you could probably derive or prove this to yourself, is multiplying it by 2 pi and then divided by 60. And so, the rationale for that is the R in RPM stands for revolution. It doesn't stand for radians. And so RPM, revolutions per minute. In one revolution, we know there's 2 pi radians in a revolution. So what we're doing is converting, first of all, from the revolutions to radians by multiplying by 2 pi. And then the m, of course, is minute, and we want our angular velocity to be in terms of seconds, so we have to divide by 60. So multiply by 2 pi, divide by 60, and then that will give us radians per second out of the RPMs that we're usually starting with in problems like this. So remember, all of the things that we've been talking about in Chapter 4 are the pressure and elevation responses to an acceleration. Because prior to Chapter 4, we were talking about static fluids, and now we're talking about the different ways that fluids move. They can either move in a uniform versus non-uniform way, and of course it is the uniform versus non-uniform is Bernoulli's equation, which we observed in the lab yesterday, where we're trying to find out how pressure changes because of changes in velocity. Steady versus unsteady was all about the local acceleration, and that is Euler's equation. And so now we're going to be looking at radial acceleration and how that affects pressure and liquid level. So here are two different fluids that are accelerating in a rotational way. We've just seen that video of the aquarium being spun around in a circle, a similar smaller scale application that sometimes people make for little, school science fairs would be inducing a water vortex where you combine a couple of different 2-liter bottles together, and you start it spinning, and then the downward flow from the upper container to the lower container kind of feeds the vortex, and it's kind of nice to look at. The question is, this surface, this curved surface, how could we calculate that numerically? And we could calculate it. You notice they kind of spun it a little bit to get that started. And by spinning it when it was not yet rotational, they're kind of inducing an acceleration there. And so what we would want to know to be able to describe the shape of that curve is, for each particle that we're interested in, what is the acceleration, what's the rotational speed that it's going at, and then we'd also be able to describe the pressure variation inside of this flow field. So that's the kind of calculations that we're going to be doing, and just to simplify things, we'll apply both of the example calculations we have today to a U-shaped glass tube where we're trying to isolate what is the location of the fluid and just looking at the pressure. Now here, it's the elevation of the fluid that's being affected by the acceleration. Just similar to like when we were starting with Euler's equation, the first Euler's equation examples that we worked, we were talking about an enclosed like container, and we looked at how pressure changed between a couple of locations as that container was accelerated. But we could also have an open container and accelerating it would affect the liquid level and the pressures. And so you can confine the liquid, and if there isn't any sort of a head space, like if it's totally full with water and it's confined in all of the surfaces, then it's only the pressure that changes. In this video that we just watched, it was both the pressure and the liquid level that's changing. And so to simplify, we'll just take the liquid level and confine it a bit by putting it in some U-shaped tubes. And so that's what this is. This is a U-shaped tube, and what we have is it's being rotated about the left leg, and because of that, the liquid level rises on the right, and it's lower on the left than it would have been if it wasn't being rotated. Now, clearly, if it was stationary, then these two ends, the liquid level would be at the same elevation. But because the liquid on the right is experiencing a greater acceleration than the liquid right at the axis of rotation, then the water sort of drifts outward into the right side of the tube. And you can see that here they're kind of indicating a little bit of that effect with the water surface being inclined here. So the deflection between the two is 25 centimeters, and what we can do is use this rotational flow equation to tell us how the pressure and elevation are affected by rotation. Now this looks a little bit like the Bernoulli's equation. The first two terms look familiar, but I got to emphasize this is not the Bernoulli equation, and there's a minus sign in there. You know, like I'm always trying to point out some of the common mistakes that people make when they're working through quizzes or exams, and sometimes people just get in the habit of adding terms together, and they forget that what we'll be doing, as you'll see in the calculations here a bit, is we subtract that third term in the equation for rotational flow. So what this says is that you can write it in a couple of different ways. You can write it in terms of piezometric pressure. This is in terms of head rather than in terms of pressure. So it's saying that the pressure head and the elevation head, the sum of those is affected by the rate of rotation. And if we look at this, the omega, the rotational rate, is the same for the entire system. It's all rotating at the same number of radians per second, although there may be different radiuses from the center point of rotation. We're going to pick two different spots. We'll pick a location 1 and a location 2 to apply this formula at. And what we're saying is that there is conservation in the head that can be described, that can be explained by the rate of rotation and the position. So just to get a first taste of how this formula works, based on how it's deflected right now, 25 centimeters, and you can see at the bottom it's saying that these two legs are 10 centimeters apart. Let's go through the process of calculating the rotational rate, omega, and that'll be in terms of radians per second. And then once we know that, we'll go and reapply the formula for radial acceleration. So here's our radial acceleration formula. Let me write it on the whiteboard so we've got it handy once we start this calculation. The radial acceleration, tangential velocity squared divided by r, and it's also the rotational rate squared multiplied by r. Okay, so in this example, what we're going to want to calculate is rotational rate, how much acceleration is experienced by this right leg based on its location being 10 centimeters away from the center point, and then what is the tangential velocity in the right leg. Okay, so what we have to do first of all to apply this formula is pick a location 1 and pick a location 2. And anytime you are using either Bernoulli's or the Euler's equation or here for rotational flow, a good hint on what to choose for location 1 and what to choose for location 2 is pick locations where you know something. Otherwise, you'll have too many unknowns in your formula. And so where do we know for example, where do we know different pressures, elevations, and radiuses? Like, we could apply this formula anywhere in the water, and it's going to be able to tell you the pressure and elevation response to the spinning that's going on. But where do we know things? At the interface, because you'll notice that these tubes are open to the atmosphere. And so here at the interface of the air and the water, we know the pressure. And so that's a good place for us to choose as location 1. So let's make location 1 be this spot on the left, and location 2 be in the right leg. And so again, not only do I know the pressure at both of those spots, I know that P1 is equal to 0, and I know that P2 is equal to 0. I can also set an elevation datum. I can say let Z1 equals 0, and then if that's going to be my elevation datum, if this liquid level is going to be my elevation datum, then I'm going to therefore cause Z2 to be 0.25 meters. So thus Z2 is 0.25 meters. Any questions so far? Okay, so if you, let me just open up this PDF here. If we write the rotational flow equation, so P1 divided by gamma plus Z1 minus omega squared R1 squared divided by 2G is equal to P2 divided by gamma plus Z2 minus omega squared R2 squared divided by 2G. Okay, still thinking about it. We know P1, P2, Z1, Z2. Now, this dashed line that I'm drawing is all the radiuses are going to be measured from this axis of rotation. So R is how far side to side we are from the axis of rotation. So R1 is going to be 0 since it's right on the axis of rotation. And R2, since the dimension was given that it's 0.10 meters wide, this U-shaped tube, then that makes R2 is 0.10 meters. So now we can start substituting things into the equation for rotational flow, because our only unknown at this point is the rotational rate. Yeah, here we are. Okay, so let's cancel out where we know terms. P1 was 0, so I'm going to cancel that term out. Z1 was 0, cancel that term out. R1 is 0, so this term cancels out. So far we've canceled everything from the left-hand side of the rotational flow equation. P2 was 0, Z2 is not 0, and then we also have a non-zero value for R2. So if we rearrange that equation, it is Z2 is omega squared R2 squared divided by 2G. And we transform that because what we're trying to find is the rotational rate. So we just rearrange that algebraically for the rotational rate omega. It's going to be 2G Z2 divided by R2 squared, and we got to take the square root of that because it was omega squared previously. All right, well, let's start substituting values that we know. We're working in SI units, so it's going to be 2 times 9.81 meters per second squared times Z2, 0.25 meters, and then divided by R2 squared, so 0.10 meters squared, and we have to take the square root of that. I bet probably everyone has their calculators today, right? see if you can calculate what is the rotational rate, and what we're going to get out of this is radians per second. That'll be the units. But what is the number you get? Anyone? 22.16? I think it should be 22. 22.15 is what I got. 22.15 radians per second. If we wanted to convert that into RPM, let's just go through that process, remind ourselves that we would have 22.15 radians per second, and then multiply that by 60 seconds per minute, and multiply that by 1 revolution is 2 pi radians. And so what we're talking about is 211.5 revolutions per minute, or RPM, if we needed to convert between the two. Okay, the next part of the example, this was the part A, is what's our rotational rate. So here's the answer to part A. Part B asked, what is the acceleration in the right leg? So over here at location 2, how much acceleration is being experienced? So the radial acceleration in the right leg will be omega squared times r. Okay, so that is 22.15 radians per second, and we square that, multiplied by the radius. And so from the axis of rotation, it's rotating about the left leg, it's 0.1 meters over to the right leg, so we're going to multiply that by 0.10 meters, and it is 49.05 meters per second squared. Okay, that is the acceleration in the right leg. And then tangential velocity. If we know the radial acceleration, we can calculate the tangential velocity. V sub t is r times omega. V sub t, yeah. So if we're solving for v sub t with this, we would move the r to the right-hand side and then take the square root of it. So it's just the radius and the rotational rate. So 0.10 meters is the distance. The rotational rate was 22.15 radians per second. So it's 2.215 meters per second. And that is, the particle that's here in 2, if we look down from above, it's circling around. It's going in a circle. And so the speed of that as it rotates, if we had like a speedometer of some sort, it would be going 2.215 meters per second. That's the tangential velocity as it is rotating. So that's how some of these pieces fit together. Any questions about this illustration before we move on to one that's a little more complicated?
The radial acceleration was going to be expressed in radians per second, or is it specific to the
The radial acceleration will always be length per time squared, but the rotational rate, omega, will always be radians per second. It always needs to be, to use in this formula, it has to be radians per second, regardless of whether you're in traditional or SI units. You can't put it into here in RPM. Are there other questions? Okay. So this tube was open to the atmosphere, and so the liquid level changed. Let's look at one where it's closed, and what that means is that although the liquid levels aren't changing, the pressure still is reacting as it spins. So we've got a couple of things going on here. The axis of rotation is at a different spot than one of our points of interest. So we won't be able to cancel out the R1 term like we did in the previous example. What we want to do is we want to find out if we know the pressure here in the left leg at location L, if we know the pressure is 2.75 kilopascals, and this is enclosed with oil, and so this isn't water. So here any fluid properties like unit weight are going to have to be set according to the specific gravity that's specified, 0.85. We want to know what's the pressure at M. So think about it. If it was static, if it wasn't spinning, then the pressure at M, would it be higher or lower than the pressure at L? It would be lower because it's not as deep in the fluid. You know, pressure increases as you go down through fluids, static conditions. Static conditions, since we would be going up to get to M, the pressure would be less. But in this case, let's think qualitatively. So the fact that it's at a higher elevation means we should expect the pressure to be less at M than L. But now what about the rotation aspect of it? Which one do you think is going to have more pressure? What if we were just talking about same elevation, but over here? Oh, I'm so tempted to draw on that. I'll just use my cursor instead. What about right here? If it's spinning at 25 RPM, what has more pressure, L or where the cursor is? Why? You're right, but why? Why does L have more pressure than where the cursor is? Higher radius. Yeah, it's further away from that axis of rotation. So more radius means more acceleration. More acceleration means more pressure. So the pressure increases in the opposite direction of acceleration. So the direction of the acceleration is towards the center, but the magnitude of acceleration is greater here because it has a greater radius. All right. So location M should have less pressure for two reasons. Because it's higher in elevation and because it's not as far away from the center line as this location L is. So when you crunch the numbers, you kind of already know what to expect. The pressure should be less than 2.75 kilopascals. But what you can do is you can substitute all these known values into the formula. Of course, you're going to have to convert from RPM into radians per second. But once you do that, then you'll be able to solve for P2. You know, if we say that location L is 1 and location 2 is M, what we want to solve for is P sub M. So I'm going to stop talking, give you some time to work on that, check with your classmates, make sure you're all headed in the right direction. The two things that you're going to have to keep in mind is the conversion into radians per second and then setting your elevation datum. It can be any place you want, but for both location 1 and location 2, you have to be measuring the elevations according to the same datum for both locations. All right, so what I did was I said let's have L be our elevation datum. So ZL is 0 and ZM is 0.125. Okay, the unit weight is just 0.85 times the unit weight of water, so that's where this 8338 comes from. We convert from RPMs into radians per second by multiply by 2 pi and divide by 60. And now we're ready to start rearranging things. Rather than just substituting in directly, I rearranged things algebraically in this case. So you can see that the pressure at location M is going to be as follows. Now don't lose track of the fact that this rotation rate term is minus, whereas we get in the habit of adding things because of Bernoulli's equation. So when you do all those substitutions, by the way, you need to convert from 2.75 kilopascals into 2750 newtons per meter squared if you're going to divide by the unit weight in terms of newtons per cubic meter. So it should be about 1339 pascals at that location. And that matches what we were expecting. Remember, we were expecting the pressure would be lower for the dual effects of it's higher in the fluid and its radius from the center line, the axis of rotation, isn't as far as that point on the left. So it is lower. The pressure is lower, which is what we expected. Good. Lots of potentials for errors. You know, these are calculationally intense, and so you got to double and triple check your calculations if you want to avoid those little 1 and 2 point deductions on a quiz or an exam, because it's easy to make mistakes on these problems because there's so many steps. Yeah, Connor.
So earlier you said that radians isn't really a unit.
Yeah, right. Yep.
So, like, I got kind of twisted around, so I couldn't get rid of my radians, which I kind of forgot you said that.
Yeah, so just think of the rotational rate just as inverse seconds. Instead of radians per second, it's just inverse seconds. Yeah. And I don't fully understand that myself, to be honest. You know, like if a rotation is 2 pi radians, you'd think that it's something, but it's not. It's not a real unit. Otherwise, these formulas wouldn't work, and we know they do. We just saw an aquarium getting spun around, so that proves that the equations work, right? All right. Are there other questions about this example? Okay. Let's look at one more. Okay, this one. What we did already was we said, let's find out what the rotational rate is based on the observed deflections. The second example, we found a pressure change due to the rotation. Now this is open to the atmosphere. So it's not an enclosed tube. So since it's an open tube, the water level is going to rise on one side and fall on the other. So which side is the water going to rise on? It's going to rise on the right. Why is that? Why is it going to rise on the right? Further radius means that there's a greater acceleration in the right leg than there is in the left leg. Okay, well let me ask you this. If it raises by 1 centimeter on the right, how much does it lower on the left? I mean, let's assume that the tube has the same diameter everywhere. So if it goes up 1 centimeter here, then what happens on the left side? It goes down 1. I mean, there's just a certain amount of liquid in here. So if it goes up 1 here, it's going to go down 1 on the left. Now, the reason I mention it is that in this problem, we don't know what are the elevations when it's spinning. So let's look at, what's the hint I told you for picking location 1 and picking location 2? Like, how do you know, what's a good spot to apply this formula? Where you know things. Yeah, you apply it where you know as many things as possible so that you can solve for what few unknowns remain. So let me do a sketch of this. When it's spinning, conceptually it's going to look like there's a little more water on the right, a little less on the left, and here it is spinning. Here's our axis of rotation. Let's call this location 1 on the left, location 2 on the right. Okay, so what do we know and what we don't know for substituting into this formula? P1 and P2. What are the pressures if we pick these, the interface of the air and the water as location 1 and location 2? 0. So it's just atmospheric pressure, so we're working in gauge, so we say the pressure at both is 0. Okay, what about the radiuses? We know that from the drawing. R1 is going to be 0.18 meters. R2 is going to be 0.36 meters. Okay. Rotational rate is given, and it's even in radians per second, so that makes things pretty good. 8 radians per second. Okay, G we know, gamma we know because this is water. So what we don't know is the Z1 and the Z2. Well, okay, so he's making the point, good point, that what we really want to know is like how far apart they are. So like delta Z. What I'm suggesting is that what we could say is that Z1 plus Z2 is 0.36 meters. This is going to be, we're going to need a second equation. You know, the whole thing with if there's two unknowns. In this equation right now, Z1 and Z2 are both unknown. And we can't say Z1 is 0 because we don't know where it is. We can only set that as our datum when it's an actual like known location, when its elevation isn't one of the unknowns. And so what I'm suggesting is we can say Z1 plus Z2 is 0.36 because if we use the bottom leg as our elevation datum, the sum of the two Z's before is 0.18 plus 0.18. So there's going to be the same amount of water. So we don't know yet what the Z's are, but we do know one elevation in terms of the other. Like what we could say is we could say Z1 is 0.36 minus Z2. So we know Z1 in terms of Z2, and then we could substitute this Z1 back in here so that when we'll only have one equation left over. I'm sorry, one unknown in the equation. So again, the reason why I said this is because here in this equation, we've identified all the things we know, but we're still left with Z1 we don't know and Z2 we don't know. So you can't have two unknowns in an equation and solve it. You need some other way of simplifying it to a single unknown. And I'm suggesting that what we can do is we can say that the two elevations together are 0.36. All right, so again, I'm going to pause, allow you to start making the substitutions, and solve for the equilibrium water elevation. So that means we want to know what is Z1 and what is Z2, and we're going to be measuring those elevations relative to the bottom of this U-shaped tube. Okay, so I have the solution up on the screen there. When we rotate it at 8 radians per second, then the elevations are going to set up such that the liquid level on the left will be down to 0.0215 meters above the bottom, and the liquid level on the right is going to rise up 0.3385. And if you add those two elevations together, then it does work out to be that the sum of them is equal to 0.36 meters. So if we lose liquid on the left, we're going to be gaining liquid on the right, and so on. Yes?
This is one of the tests.
Mm-hmm.
I would have put 0.34. Would that have points off? Or?
No. Nope. Other questions? All right, so the slide then poses the question, this was originally at 8 radians per second. What happens if we keep spinning it even faster? So it's almost kind of like maxed out in a way. Like there's very little liquid in the left. Most of it got pushed over here to the right. And it can drop a little bit more, but just think about physically. Like, you know, you've seen things, you kind of have an instinctual guess for what happens if we spin it even faster. Well, eventually it could spill out, but let's say, you know, it's not there yet. We've still got plenty of additional headroom. What happens to the liquid level on the left? It can only go down to 0, right? We can't have a negative number. Like, I mean, numerically you could. Like, you could start crunching the numbers and get a negative z. And in fact, if you do that, if you try and just directly substitute in, instead of 8, if you try and substitute in 14, then it'll give you a negative z value. Let me just show you what I mean about that, because I've done these calculations as an illustration. So if you had a rotational rate of 14 radians per second, so everything's the same as it was before. We just switch from 8 to 14. Then you would get a Z2 of 0.665, and if you substitute that back into our Z1 is 0.36 minus Z2, then it would say that there's some negative value for Z1. But like just the tube itself is constraining the liquid where it can't go any lower than that bottom base leg. So that's not possible. So what it actually means is that if we go back to the physical reality of this setup, if you spin it faster and faster, what happens is that it goes down to 0, and then the liquid level starts getting closer to the center line of rotation. And so it's still rising on the right, but that liquid is now over in the base leg. And so this problem actually, once you start spinning it fast enough, originally Z1 and Z2 were the unknowns. But then when the liquid level is down in this base leg, the Z1 is known, but what isn't known is the radius. So the two unknowns will be Z2 and R1. And so let me show you, using this 14 radians per second as the illustration, what those calculations look like. So we started off by recognizing something's not right. We can't just substitute it back into the same formula that we had before because we're getting a negative Z1 value, and that's not possible. So we got to think outside the box. And so here's what the setup looks like. It looks like we've got location 1 becomes here in the bottom base leg where we know the elevation but we don't know the radius. And location 2, we still do know its radius, but we don't know its elevation. So we have to come up with some new formula that relates z and radius. So I told you this one, Z1 and Z2 was 0.36. And if we go back to the original sketch, we can come up with something that relates the radius and the elevation Z2. So think about how much water is there total. There was the 18 in the left, the 18 on the right, and then 18 down here, 0.36, meters. And so when By the time the liquid level is down to the bottom, then we've got 0.36 on the right. So all of this liquid on the left is now over on the right side. And now each additional unit of centimeter that it gains means that the R1 is decreasing. So what I'm saying here is Z2 is 0.36 because all of the vertical liquid is in the right. And then it's also going to be 0.18 minus R1. That's the formula that will relate Z1 and R1. So 0.18 minus R1. Let's see if that makes sense. So 0.18 minus R1. So if R1 is 0.18, then that means the Z2 is just the 0.36. So if the radius is all the way out to the edge, then we know there should be 0.36 in the right. And then any additional centimeter that the liquid level retreats towards that center line of rotation, then that'll increase it on the right. So I think that formula does work out. It gives us what we're going to need to relate the radius and the elevation. So now 14 radians per second. We just are canceling out different things. We still know that the pressures are 0 and cancel that out. This time we get to cancel out the elevation on the left, but the elevation on the right doesn't get canceled out. And so now we make the substitution for Z2 in terms of R1. And you go through the substitutions in the algebra. It turns out to be an equation that has multiple roots. And so the radiuses, the roots of the equation are negative 0.2293 and 0.3294. And 0.3294 actually won't work because the maximum R1 is 0.18. A negative R1 simply means that the liquid level is actually retreated to this point where it's further to the right. And so it's all the way, instead of being a positive value, a negative value simply means that it is to the right of the axis of rotation. So you'd think that the negative root would be the nonsensical one, but actually it's the positive root that's the nonsensical root. And so the reason why I've showed you this illustration is I believe there's a homework problem that you have to think creatively like this, and you have to relate the elevations in terms of a retreating radius. And so this process is what you'll need to apply on that homework problem, if I remember correctly, that you've got one a little bit like this. Any questions? Okay, well, it's on the video if you need to come back to it. Let's just look at the key ideas for one of these problems, problem 490. And I pointed out because you look at it and you think, oh, this is one of those rotational problems. You know, you open the drain on a bathtub and it starts spinning around in a circle. But this is an irrotational flow problem. Irrotational means not rotational. So actually, you're going to be using Bernoulli's equation in this problem to find the pressure difference between 2 points, point A and point B. The book, by the way, the first bullet point is calling 62.4, it's calling that the density. That's actually the unit weight of the liquid in terms of traditional units. Remember, density is 1.94 slugs per cubic foot, but this is a gamma that the problem statement tells you. Okay, so the hint that I'm giving you is even though the hole at the bottom of a container would maybe make you think it's swirling around in a circle and you should apply the rotational flow equation, this one is actually a Bernoulli's equation problem. All right, that is it for today. Let's just refer back to these announcements and remind ourselves the homework assignment is due on Tuesday. So if you have any questions, please feel free to stop by my office or send me an email. I will see you next week.